If physicists heard a rumour that football fans were saying you can't be a football fan and a scientist, we would be scrambling like crazy to get some conversations going. We would have scientists in residence in every football club in the country. We would be sponsoring, publicity at half-time at every major football game. We would be just jumping to it to say, no, you can be a football fan and be a scientist. Of course you can, there's no problem.
Welcome to People Doing Physics, the podcast that explores the personal side of physics at the Cavendish Laboratory at the University of Cambridge. Hello, I'm Charlie Walker, an astronomer at Cavendish Astrophysics.
And I'm Vanessa Bismuth, Communications Manager at the Cavendish.
Today in People Doing Physics, we're excited to welcome Russel Cowburn, Professor of Experimental Physics at Cavendish Laboratory, serial entrepreneur, and a man of faith, newly appointed the Canon Scientist at St Albans Cathedral. Russel's journey to becoming a physicist started with a light bulb moment, quite literally. From his early interest in electronics to his education and career in Cambridge, with a couple of detours through engineering in France, his profile sits at the intersection between science and technology. With over 60 patents granted, Russel is a master at translating discoveries into technologies. The emergence of nanotechnology, the manipulation of matter on a tiny scale, in the late 1960s shaped his research approach, recognizing the need for collaboration across disciplines and the importance of technology transfer to solve real-world problems. In that spirit, he's founded 3 companies, including one focused on nanotechnology instrumentation and another aimed at speeding up drug discovery, reflecting his commitment to applying science to the needs of our modern society. Together, we talk about the oh-so-important ability to pivot in science, standing on the shoulders of giants, and his engagement in bridging science and faith. Stay with us. So welcome, Russel, and thank you for joining us today.
My pleasure.
And let's start, as always, at the beginning. So do you feel that there are any formative moments for you that marks the point where your interest in physics began?
I think for me it all began at about the age of 3 or 4 when my parents bought me a toy garage which had a little illuminated light, a little sign on top. And within minutes it was obvious to me that I had to take this apart. I had to disassemble it and find out how that light worked. From there, my father showed me how to light a bulb using a battery and a couple of pieces of wire. And that was one of the most transformative things that's ever happened to me in my life. That once I could see how to build a circuit, I was off. There was no stopping me.
Where is that fascination for physics? Was that ever expected? Like, do you come from a family of scientists? Do you have any precedents? Was that your character only?
Yeah, I mean, I come from fairly humble roots. My grandfather was a coal miner, and my father left school very young. Having said that, he worked in electrical engineering all of his life, and so there was clearly something there that worked with technology engineering. So I think, yes, my genes are partly responsible, but I'm certainly not from an intellectual family, if you like. I was the first person in my family to go to university. And so, yeah, I don't think anybody imagined that I would end up being a professional physicist. That wasn't something that anybody had ever done before in my family.
So you mentioned before that you began building much more sophisticated electronics at an early age. What were the highlights? How did you put them to use? What did you do?
Well, I mean, if you saw my early teens bedroom, it was indistinguishable from a lab here in the Cavendish. I had soldering irons. My father managed to salvage an old oscilloscope that was being thrown out at work, voltmeters, all that sort of thing. I became obsessed for several years with building burglar alarms. I have a sister who's 3 years younger than me, and so obviously she had to be kept out of my room, and electronics was my solution for that. But also there was a science fiction program called Blake 7 in the 1970s, and I became obsessed with this, and I set about trying to recreate all of the technology that they had in that television program, again with bulbs and wires and switches and things like that.
So was your father happy to buy you all the stuff to do these things, or to lend you these things? And
within reason. I mean, actually, money was very tight in my family, so there wasn't much buying of things like that. I had a more distant family member who worked in a battery factory, and he was responsible for testing batteries. And so when he finished testing them, he was allowed to bring them home. And so he was my supply of batteries. And that kept me going, because in those days we didn't have benchtop power supplies and batteries were quite expensive.
so tell us more about the transition from doing electronics as a hobby at home to learning it at school. Did turning fun into work take anything away from your enjoyment of physics?
I mean, for the first half of my school time, up to the age of 11, I didn't do any science at school. The first half of my schooling just didn't have science on the curriculum. So it was really aged 11 was the first time I was exposed to any sort of formal science, and in particular physics, and I just loved it. I had quite a strict teacher. He wasn't particularly fun, he wasn't particularly inspirational, but he was rigorous, and I think that really worked for me. So, just learning the basic concepts, the basic equations of physics, I adored it. I really came alive with it.
So it actually brought more fun than remove any of the fun.
It did, but in a very unusual way, actually. It certainly wasn't what we would consider fun, as in lots of explosive experiments and that sort of thing. It was very much an intellectual thing, but it really worked for me. Just to see the beauty of the equations and to see the coherence and the consistency of physics. I remember one key moment where we'd been studying Newton's laws, and in my mind I could remember sort of anticipating the concept of momentum. That word hadn't been used and we hadn't been taught that, but I could see from the way that everything was building up and pointing that way, there must be this thing out there that I would now know is called momentum. And then in the next lesson, when we were taught that, it all made perfect sense. And for me, it's that coherence, that consistency is one of the joys of physics. And the fact that it explains the world we live in so very well.
And were there any aspects of physics which you initially struggled with? What did you work on?
I mean, I guess as a physicist, I'm not particularly mathematical. There are some physicists who are really mathematicians, and the distinction between maths and physics is very hard to find. There are other parts of physics where the distinction is clearer, and I think I'm that sort of a physicist. I mean, I'm competent at maths, but it's not something that comes quite as naturally to me as some of the other people in the Cavendish here, for example. And that's probably why I've ended up working in a part of physics that doesn't really need too much maths.
And so, then you ended up in Cambridge doing an undergraduate degree. And interestingly, you told us earlier that you didn't initially choose to study physics at all. So could you tell us more about what you did initially choose to study and why?
Yeah, so I actually came to study engineering. I think this is a problem a lot of A-level students have, that engineering is not taught as an A-level in most schools. And so you've got the choice between physics, which you know what that is, or engineering, which you don't really know what that is. And so that can be a difficult choice. On reflection, I probably made the wrong choice at the time, because about 6 weeks into that course, I realised that I would be having more fun if I were doing physics. And so I changed courses, which it was great that the university had the flexibility to let me do that. In reality, looking back on it, I think my interests are exactly on the interface between physics and engineering. And so it's not too surprising that as a teenager, I couldn't quite decide which way to jump. And in my day-to-day work now, I probably do as much engineering as I do physics. So I think I'm meant to sit on the interface, which it's a great place to be.
But why did you want to switch? Was it too mathematical? Was there another reason behind that?
I think it was a question of emphasis. I mean, certainly at degree level, first year physics, first year engineering, they're not so different from each other, but they do have a slightly different emphasis. The physics emphasizes the underlying phenomena and the why and the how, whereas the engineering focuses more on how to actually use it. And although I'm hugely passionate about using it, I also really wanted to know what was under the bonnet. I really wanted to see at a deep level how electrons and phonons worked. And I wasn't quite getting that in engineering.
You found they were stopping slightly short.
Yeah, I think that's right. It was just not quite focused on the bits that I really cared about, and it was putting a bit more emphasis on the things that at that stage I wasn't quite so interested. I remember, for example, doing a first year engineering problem where we had to work out the strength of materials, and I mean that's a very physicsy sort of thing. But then we had to divide that strength by the cost to get a strength per unit cost. And at that point, I thought, well, that's a very strange thing to do. That's not a very physics way of looking at the world at all. But it's a very important engineering way. Otherwise, we'd build all our buildings from, gold or something like that. A completely impractical solution.
And in practice, how did you find that switch? Was it easy? Was it hard? Did you require extra support? What did it involve?
I mean, I'd missed some important stuff. Although I say physics and engineering are fairly similar in the first year of a degree course, there are some things that are completely new. So, for example, in physics, we did special relativity, the properties of things moving close to the speed of light, and engineers don't study that. And so I had some catching up to do there. I got a huge amount of support from my college in Cambridge, St John's, so they gave me extra supervisions. And by Christmas of the first term, I was pretty much caught up again.
And you enjoyed that because relativity is quite mathematical, right?
Yeah, I mean, there are different flavours of relativity. There's special relativity, which is about things moving near the speed of light, and there's general relativity, which are things that are very heavy in gravitational fields. Special relativity is a little bit less mathematical than general, and it's no surprise that I found special relativity more interesting than general, which is probably why, as a physicist, I've ultimately ended up looking at materials and electrons where general relativity isn't important, but special relativity can be important. And I'm not an astronomer, for example, where general relativity on the scale of planets is very important.
So it sounds like you settled well into physics. You found your home.
Yeah, that was my thing. Yeah, absolutely.
But this is only part of the journey. Were there any formative moments during your undergraduate which led to focus on nanotechnology, where you are?
Well, in the degree that I did, in your second year, you had to choose between doing a long experiment where you came back during the summer and spent a week doing one experiment. Normally, in an undergraduate degree, you only spend 3 or 4 hours at most on any one practical class. So to do an entire week, that's a new thing. So you could choose between doing an experiment or doing some extra maths. By that stage, I knew I wasn't hugely strong at maths, and so I chose the experiment. And I must say, whereas a lot of my colleagues found this torture, they had to come back in the summer and do a week of experiments, I just loved it. I remember I was trying to measure the specific heat capacity of a gadolinium rod. No idea why, but that's what we were doing. And I became obsessed in that week with just getting one more significant figure in the accuracy of the measurement. And that was really when I began to see just how exciting experiments could be and how absorbing they could become, of trying to refine the experimental technique just to reduce the errors and just to get the most accurate measurement possible. So I think that was quite a key moment. The other key sort of academic moment was in my final year, I had to choose a short research project. I must say, compared to today's students, I didn't spend much time choosing. I quickly looked down a list. I saw something that had lasers and thought, oh, that sounds quite fun, and chose that. And again, that was an experimental project where we were trying to reduce the noise level on a laser measurement system. And that really fascinated me as to how to design control loops and filters and things like that to eliminate the unwanted noise and to make the signal better. I think by the end of the experiment, my signal to noise ratio was about 100 times better than it had been on the experiment I'd inherited. And that was
success.
That was very satisfying indeed.
Was it so satisfying that you decided to continue? Didn't you ask to pursue with them, or were you asked?
No, in those days you asked.
Yeah.
In those days, it was relatively easy to get a PhD position. And yes, even though I hadn't spent much time choosing that subject, I really enjoyed it and thought this was something I could spend more time doing. So I asked if I could stay on and do a PhD.
But you did ask to take a break in between. Tell us about that.
I did. One of the little sort of side hobbies I'd had as a student was learning French language.
As you do.
As you do. Well, it's a wonderful language, as you know, Vanessa. And I was the very first year to do an AS level. It was the experimental year of AS levels, where you could do a subject to half of an A level. And so I chose to do some French on the side. I really enjoyed that, and so I continued it at university. I joined the first year undergraduates for their French language lectures, which was entertaining. And so at the end of it, I spoke French reasonably competently, but as in a textbook. What I really wanted was to learn to speak like a French person, which you don't get from a textbook. For that, you have to live in France or a French-speaking country. So I found my would-be supervisor and said, I'd like to go to Paris, work in a bar for a year, just to learn French properly. When I come back, could I then join your group, please, and do a PhD? And remarkably, he said, well, that's fine, but I have a collaboration with the University of Paris Sud in Paris. If you join now, I can arrange for your first year to be in Paris. That way you get to learn the language, but you also get to start on your PhD straight away. So I did that. And so I packed my bags and went to Paris and did very similar experiments, actually, but in the French lab.
And how did the French go and learning French?
It was a French-speaking lab, so I worked all day long in French. I reached a stage where I was dreaming in French, which that's, for those who learn foreign languages, that's the two key things in learning a foreign language are when do you start... Key stage, when do you start dreaming, and when can you confidently answer the telephone? Those were the two milestones, and I passed both of those. And it was also a great experience academically, because certainly at the time in Cambridge, I would have been about one of 13 students with a single senior scientist. In the French lab, it was the other way around. I was the only student, and there were 5 senior scientists. So I had all these people with a lifetime of research experience and knowledge, and so that was fantastic as well.
So how did you find the return to the UK then, and to that one PhD for or one PI for 13 PhDs?
Yeah, I probably had some sort of culture shock from it. I think I was probably quite a difficult student. I think my supervisor didn't enjoy having me that much, because I'd had a slightly different introduction to research life. But I got good experimental results. Most students find that across a 3 or 3.5 year PhD, there's only 1 year when the data are really flowing and you're really getting lots of new data. The rest of the time, either things aren't working or you're preparing to do the experiments. And for most people, that happens around year 2, 2.5. For me, I got most of my data in the first year. So I came back to Cambridge with several logbooks absolutely brimming with data, and then finished off and then wrote the thesis from there.
So tell us a little bit more about that data. What kind of experiments were you doing?
So as you said at the beginning, Charlie, I was interested in nanotechnology. We didn't call it that in those days, but essentially it was. And I was particularly interested in magnetic materials. And what happens if you take a material that you know is magnetic in everyday life, like iron or cobalt? What happens if you take that and you make it really, really thin or really, really small? So I was working on samples that were just 2 or 3 atoms thick, but made of mainly iron. And really just asking for the first time, are they magnetic? Does magnetism exist on the atomic scale, or do you need to be above a certain size before something becomes magnetic? And if it is magnetic, is it the same sort of magnetism that we experience in a fridge magnet, or the sort of magnets we know in everyday life?
And it's really interesting that you say it wasn't called nanotechnology back then. From what you've been telling us, it sounds like that field and the development of that field really coincided with your development as a researcher. So could you tell us a little bit more about the concept of nanotechnology as a broad church, and how that came to develop and how you became involved with it?
Sure. So nanotechnology is really the science and the engineering of the atomic scale. So it's everything from 1 atom in size up to a few thousand atoms in size. And at the time, physicists would call a lot of that type of research surface science, because you do a lot of these sorts of experiments on the surface of another material. It turned out, though, that at the same time, chemists were also thinking about things that were a few nanometers in size, but they called it macromolecular chemistry. And biologists were thinking about things on the nanometer scale, but they called it cell biology or molecular biology. And so actually very different routes, but we all had in common the fact that we were trying to understand how the world works on the near atomic scale. And around the late 90s, we all met each other and realized we should really collaborate a bit more because we were all using the same techniques and the same length scale, even though we were looking at very different problems. And that sort of big tent of collaboration between physicists and chemists and material scientists, biologists, that became known as nanotechnology. But as you said at the beginning, its roots really go back to the late 1950s, when the Nobel Prize winning physicist Richard Feynman gave a lecture called There's Plenty of Room at the Bottom. And that was when he started to just think about how small can we go today and what are the ultimate limits, and realized there was a big gap between the length scales that scientists were working on in the 50s compared to the ultimate limit of a single atom. And he was the one that really realized there was a lot of really exciting science and a lot of exciting technology to be found in that gap at the bottom.
And is a single atom the ultimate limit? Are we there, or is there more? Is there deeper to delve?
I mean, there are limits and there are limits. Obviously, if you talk to a particle physicist, who studies the inside of a single atom, or if you go to CERN and look at the Large Hadron Collider, they would say an atom is huge, that they don't even get excited until you're, millions of times smaller than a single atom. I guess what I'm thinking about is the level at which you could practically engineer things and make a device, make something useful out of it. And at least by today's standards, one atom is about the limit for that. We can certainly go to one atom. It gets a bit painful. At the one atom scale, you're really still pushing the limits a little bit. We tend to do more things at the 10 to 100 atom scale, but there's a lot of really great science to be done there still.
And you spoke about collaborating with chemists and biologists as well. And it seems like collaboration with experts from other areas is kind of a theme that's leaked into other parts of your work as well. So, for example, you have a keen interest in technology transfer and working with industrial partners. So could you tell us how and when you started doing this and why?
So I published a paper in the late 90s that got quite a lot of coverage. I'd sort of found a new way of doing electronics that didn't actually use any conventional electronic components. It used a completely different approach. And although ultimately it wasn't hugely useful, it's interesting to think about, could we build an entire technology in a very different sort of way? And that paper got a lot of publicity, and I got a telephone call one morning from an industrial investor saying he was quite interested in this and could he come and meet me and that he might like to invest industrially in this technology. And I said, sure, let's meet next week. And just as a point of conversation, I said, where are you coming from? Thinking you'd say London or maybe Oxford. And he said, Dubai. And it turned out that he represented a consortium of wealthy investors who were looking for very early stage technologies to invest in. And they put quite a lot of money into my research. And that was the first time I'd sort of had a high level collaboration with industry like that. And we worked together for many years. And that then led into medicine. So I started collaborating with surgeons, both in America and here in Cambridge. So yeah, a fairly broad range of people actually.
So how did this sort of shape your approach? Do you start with a solution and look for applications for it now? Or do you start with a problem and see where it goes?
Yeah, I mean, all of the above. We talk about market pull or technology push. So market pull is when you start with the problem and you say, how do I solve that? How do I get clean water to people in the world who don't have it? How do I reduce carbon footprint of carbon intensive industries? The technology push is where you say, I've got this really cool technique with electrons. What's that useful for? In general, people say market pull is better. I don't know if that's true. I think you need a bit of both and you've got to meet in the middle. And certainly finding that meeting in the middle between the market pull and the technology push is really difficult. But that's the secret sauce. That's where the magic happens, when you can find a really nice new technique that solves a real world problem particularly well. That's the best place to be.
And that's why we were talking about the concept of pivoting and like the importance of being able to see, to pivot and to like something that you were thinking would be useful actually turns out to be not so useful, but could work very well in another. Can you tell us Can you expand on that a bit more?
So quite often when you're trying to match a societal need or a problem the world needs solving with a really cool new bit of science, quite often you get it wrong first time. Either you use the wrong bit of science to solve the problem, or you haven't found the best application of that science. It can solve a different problem better. So for example, before when I talked about a paper that I published on a new way of doing electronics, I thought that would solve the problem of how to reduce the power dissipation of microchips, how to make batteries last longer in mobile phones, for example. It turns out it doesn't, but what it does do is help you make a better braking safety system in a car. I had no idea of that. So in reality, you need several attempts when you match up a problem with a solution, and changing your mind is what we call pivoting, where you take the same technology and apply it in a different direction, or you try to solve the original problem using a different bit of science. And most sort of early stage companies, most spin-outs or startups, go through several rounds of pivoting before they really optimize the match between the problem and the solution.
So I'm talking about that early like startups. What challenges are there for scientists who want to develop their societally useful applications for their potentially abstract research? Do you have any advice for them?
One of the great things about being a physicist is that we believe that ultimately we can do anything. Physics gives you a really fundamental training, and in principle anything else can be extrapolated from that. So a lot of scientists are put off by the fact that they don't have a training in business. They say, well, I went to university and did physics or chemistry. I didn't go to business school, therefore I can't possibly start a company. I think the confidence that physics gave me allowed me to say, well, I've done quantum mechanics. How hard can business be? Surely we can work it out.
Fair enough.
And but I think for a lot of people, there is a barrier of saying, I'm not a business person, therefore I can't do anything in this space. But, there is a valley to be crossed, because equally from the business point of view, the business people say, well, I'm not a scientist, so I don't know how to introduce new scientific discoveries into my products. And so somebody has to reach across the gap and do something that they're not necessarily expert or trained in. Personally, I've made the effort to try to take my science and try to get it across that gap and try to do a bit of business with it.
Again, sort of straddling the boundaries between two different professions or fields in the same way as with engineering and physics.
Exactly. It's a different form of interdisciplinary collaboration. And in reality, you always end up being a professional in one subject and an amateur in the other. And you've just got to suck it up and realise that you will not be as expert in the other area as some of the people around you. You've therefore got to make collaborations and get to know people who know more about this. You've got to be humble and be willing to learn from them, and not be afraid to look silly in front of them.
So when we talked before to prepare this, you were saying that you feel your approach to PhD was different to the approach that your students have now, in terms of, do you feel it's harder for researchers to make new discoveries today? How has the field changed, and how do you tackle this?
I mean, the difference is that, and this is true for every generation, that when you're in the early stages of a subject, so in my case, I was asking just really fundamental questions like, are atomic scale materials magnetic or not? Can they be? You've got lots of very new early stage questions you can address, but equally your tools, the tools in your toolkit are relatively limited. So for example, in the 1980s, the decade before my own research started, a lot of that work failed because people didn't have good enough vacuum pumps. We may not think a vacuum pump is a particularly exciting sort of thing, but actually between the 1980s and the 1990s, vacuum pumps got about 100 times better, and that suddenly enabled a whole new set of experiments that had just failed a decade earlier because the materials weren't clean enough. So you've always got this tension between how many new questions are there and how developed and advanced is my toolkit. Today, it's pretty much the same. So, students studying quantum technology or artificial intelligence lots of really fundamental early stage questions to ask, but they're only just getting the toolkit to do it.
Yeah, we're talking about the development of instrumentation and the exponential development of instrumentation, making things go faster and quicker and then getting us a better understanding. Do you think that's what you're trying to do as well with your own enterprises and your own companies, like develop that kind of better instrumentation to help scientists do better research?
So Isaac Newton is attributed as saying, if I've seen further than other men, it's because I was standing on the shoulders of giants. And I think a lot about what does that mean today, to stand on the shoulders of giants? How does one generation of scientists inherit all of the work of the previous generation? And I think instrumentation, the sort of lab experiments that we build and that we hand on, are an important part of that. Because if you can start your research using an off-the-shelf piece of equipment that somebody else has taken a decade to develop, you're 10 years on day one. Whereas if you've got to develop that yourself, it will take you much longer to make progress. So looking back over my scientific career, yes, I've done my own contribution to new discoveries, but I think the bigger impact is the fact that I've developed instruments that hundreds of other groups around the world now use and allows them to accelerate their research. I was counting up the number of papers that both I published and that collaborators of mine have published. I've published 150, 200 papers, something like that, which is a normal sort of number for one scientist's career. If you look at the number of papers published using experiments that I've designed, it's about 20,000. So my personal impact has been much greater through my instrumentation development than through any one thing that I've actually discovered myself.
It's an interesting thing to take a step back in perspective to take.
And this is just one area where you have a company and you focus. And we mentioned at the beginning, I think, that you have 3 different areas, and all of them have sort of links to enabling people to do other things and faster. So could you tell us a little bit more about the other spin-outs of your research that you're particularly proud of?
So one of them was a security technology, trying to identify counterfeit and smuggled goods like passports or counterfeit currency. It was really interesting. We spent 5 years trying to convert that from a lab experiment into a real-world technology. Ultimately, we failed and the company went bust. And that is absolutely part of the spin-out experience. If you haven't had a company go bust, you're not trying hard enough. Another one, which is currently on the go, is essentially trying to reinvent the test tube for biologists using nanotechnology to help them discover drugs like chemotherapy drugs more quickly. It's going really well, but it's still relatively early days. Come back in a few years and we'll talk some more about that one.
Definitely. And so becoming a nanotechnology researcher and becoming a technology transfer industry consultant, they're just 2 parts of a much longer story. You're also a Christian. And from our previous chat, it sounds as though your journey as a Christian and your journey as a scientist are sort of intertwined. So could you tell us a little bit more about how these develop together?
Yeah, so I took a gap year before coming to Cambridge to study engineering. And during that gap year, I read the Bible for the first time, which I'd never done before, and was really surprised by what I found. And as a result of that, I became a Christian during that year. And so for me, I was a newborn Christian and a newborn physicist, both in the same year. And so my entire life, I've really been living the science and religion debate, if you like, in my head. So 30 years on, I'm still both. I'm still a physicist, I'm still a Christian. And it means that those 2 parts of my life have really intertwined and grown up together.
And as you say, some people may have this conception that faith and science are fundamentally incompatible ideas. What are your thoughts about that, the relationship between religion and science?
I mean, I absolutely understand that a lot of people think that, but if we take the longer view, we have to recognize that most people at most times have not thought that. If you look at many of the great founders of modern science, people like James Clerk Maxwell, who was one of the great founders of physics, or Robert Boyle, one of the great founders of chemistry, they wouldn't have understood that. They would say, what are you talking about? Why on earth should faith and science have any problem with each other? I mean, sometimes we think even of Charles Darwin as being at the heart of this problem, so to speak. But, if you look at Charles Darwin's correspondence, there's a nice letter where somebody wrote to him and said, is it true that your science says that I can no longer believe in God? And he wrote back and saying, of course not. There's no reason at all why the things that I've discovered about evolution should stop you from believing in God. So throughout most of science and most of history, most people have found science and religion to be completely compatible. I agree, there is a strain of thought today that says they're not, but I see that as more a historical blip, an anomaly, if you like. And I think even today, that view of incompatibility is dying away. There are just too many scientists who have a personal faith of one form or another for it to be tenable as a hypothesis.
So you that's actually a nice bridge to my next question, which was about your new role as the sort of scientist in residence at St. Albans Cathedral. Is that the sort of things that you see as getting that view about the incompatibility between science and faith reduced and go back to the original point of view that there is no incompatibility and it's all fine to live side by side?
I mean, I think incompatibility or showing that these things aren't incompatible is only the first step. I think there's a much richer and more exciting area at the overlap where we start to ask questions about how does faith help science and how does science help faith? Because fundamentally, both are interested in the nature of the world and the universe that we live in. John Polkinghorne, who's one of the great thinkers in the science and faith area, so he was a quantum physicist in Cambridge who mid-career left day-to-day research and became ordained as a clergyman. So he sort of lived this as well. And he talked about binocular vision, of saying with one eye we look at the physical world through the methods of science, and with the other eye we look at the theological world. And really to get the best view of what does it mean to be human, what is the world that we live in actually like, you need that binocular view. Whereas if you say, I only do science or I only do theology, you've sort of got a telescope view that isn't quite as three-dimensional as a full-blown binocular view is.
That's a very good way of looking at things. It's like avoiding to stop short of understanding the entirety of the world. Tell us what it means to be a scientist in residence at St. Albans.
So several cathedrals around the country do this. They create a position within the cathedral for a scientist. In my case, I'll be giving some lectures, doing some podcasts, doing some fireside chats. We're going to try to move around St. Albans a little bit, meet some different people, but essentially talk about science, because there are a lot of people of a faith background who are scared of science and they don't know much about it. So they are a community that, we'd like to talk more with and say, this is what science actually is. Talk about some of the hot scientific questions like evolution and Big Bang, but also just talk about everyday science like nanotechnology and some of the new emerging areas like artificial intelligence and quantum technology. So we're going to have a good old chat about science, but then we'll also talk about the theological implications just try to have a better conversation.
And you mentioned in our previous chat that there is a benefit to scientists as well. You had a nice little anecdote about football matches and churches. I was wondering if you could share that with us again.
So one of my favourite statistics is that there are more people in the UK, there are more people in church on a Sunday morning than there are in the football stands on a Saturday afternoon. I know that seems unbelievable, but do the maths and it is absolutely true. If physicists heard a rumour that football fans were saying, you can't be a football fan and a scientist, we would be scrambling like crazy to get some conversations going. We would have scientists in residence in every football club in the country. We would be sponsoring, publicity at half-time at every major football game. We would be just jumping to it to say, no, you can be a football fan and be a scientist. Of course you can, there's no problem. By extension, there is a rumour going around that you referred to at the beginning that if you are a scientist, you can't be a person of faith, or if you're a person of faith, you can't be a scientist. We just need to get talking and just to make it really clear that that's not the case.
So do you feel well equipped for that role? Have you prepared for it? Have you trained?
I mean, part of the problem is that actually on the scientific side, I've spent my whole life, becoming an expert in nanotechnology. But in a role like this with the cathedral, they want to talk about an awful lot more than that. And I'm not actually a scientific expert in those things. So, I'll have to talk about Big Bang. So I'm going to have to go and read a book about astronomy, because the last time I looked at astronomy was 30 years ago as an undergraduate. So I've actually got a lot of science I need to polish up on. But also, as I said before, with any collaboration, any interdisciplinary work, you end up being an expert in one and an amateur in the other. So I think of myself as an amateur theologian. I've read a little bit, I've done some studies, some courses, I'm a lay preacher, so I'm competent in theology, but I'm not nearly an expert. So, a couple of weeks ago I was giving a lecture in St Albans, and the Bishop of St Albans was there, and he asked a question, and it was quite a theological question. So, you have to get used to this professional and amateur status at the same time.
But we have this idea in science that there are no silly questions, right? A question is always a good question. It's to help inform someone. So is it the same?
It is, but equally, the two things that make interdisciplinary work difficult, either in science or between, say, science and religion, is there's a question of vocabulary. So we all use technical words that the other side don't understand. And there's the question of worldviews, of mental models. And, it takes years to build up a physicist's view of the world. And equally, theologians have spent years building up a theologian's view of the world. And it can take quite a bit of time to work out what the other person, where they're coming from, because we don't share that same worldview. Even really practical cultural things. In science, for example, the standard way of giving a talk is to work without any notes. You get a few PowerPoint slides and you make up your words as you go along. Theologians never do that. Theologians always write out a word-by-word script and they read it out. Now, to a scientist, that sounds really boring and really stilted. And equally, when the theologians hear a scientist just choosing their words at random, they think we're just really sloppy with our use of language. So there are lots of little interesting cultural tweaks that have to be overcome there as well.
But interestingly, and I think we'll conclude on that, but all of those theologists and scientists, you would be talking to people that are none of those. Your target audience is the general public, who is probably not a scientist or a theologist. So you need to find that language that is actually understandable to those people.
Yes, very much so.
That's the most important point.
Very much so. So that's exactly right. Yes, so that's another challenge. But I guess in science, increasingly we are used to trying to do that. Public engagement of science is a really important thing now in the way that it wasn't when I started out as a scientist. So many of us over the years, have begun to get a bit of experience of this. But now there's the extra twist that we've got to do it theologically as well.
That's lovely. Thank you so much for your time, Russell. It was great to talk to you today.
My pleasure.
Thank you to Russell Cowburn for joining us today. As always, if you'd like to learn more about what we discussed in this episode and more generally about our work at the Cavendish, please have a look at the show notes or go to our website. If you have any question you would like to ask our physicists, head to social media and tag us with the hashtag #PeopleDoingPhysics. This episode was recorded and edited by Chris Brock. Thank you for listening to People Doing Physics. We'll be back soon. Until then, take care.